Everybody, today we're going to continue on with the idea of solving trig equations. This time we're going to be doing some more complicated examples. One where you have to use your graphing calculator, say if it's not with a special angle that we're used to using. And then there's also the case where just the equations are a little bit more complicated and it requires a little bit more finesse, but should be a good one, so let's get into it. First off, using your calculator, so we have this question that says, suppose we have sine of theta equals 0.3, where we want the answers to be between 0 and 2 pi, as usual. So to start this off, it wants to figure out, first off, are you in radians? We want to be using radians because we are given the 0 to 2 pi. That's kind of your hint. I am in radians, so we're good there. Inverse sine of 0.3. It just says, what is that? Well, that is 3.04. Let's go 3.0. Sorry, 0.30. Rounding to 2 decimal. Oh, it says 3. So let's go 0.305. You know, it's a good one if the teacher's struggling with rounding in the first question. So 0.305 is what we get, but there's another angle. There's always another angle. So the first one is here, second one's over here. Doesn't really matter exactly where it is, but we know that there's another one over here. Your calculator's not going to give you that one. You have to figure out where that comes from. And to do this, think about the reference angle. The reference angle should be the same thing. So this is also 0.305. So I make it all the way to pi, and then I take away 0.305. So 0.305, and then pi minus 0.305 will be the second answer. So pi minus answer, and we get 2.837. So those, you will have to recognize that your calculator is only going to give you one of the two solutions, or potentially one of the 4 solutions, or one, maybe it gives you the only solution. Who knows? It depends on the situation. This is why you need to use the tools that we talked about yesterday to come up with how many solutions there should be and how do you find those solutions. So in this case, sine is the same when the y values are the same. Just make sure you can find all of those y values. So maybe you don't want to do it that way. Maybe you'd rather come up with, I'm going to kind of skip these questions and just go with my own ideas, but you could also use your graphing calculator if you don't want to deal with the options of subtracting or whatever. But we're going to put in sine. We're going to put 0.3, and then we're going to put sine of x in there, and we're going to graph that. Beautiful. Beautiful. Yes, yes. Perfect. Okay, so there's a couple of issues going on here. One, my range is off. So I'm going to change this. You know that sine doesn't exist outside of -1 and 1, so just make sure you can only see that. I'm going to go -1.5 just to give us some room, and then 1.5 for that. Alright, so issue number 1 is fixed, but as you can see, we're about to hit more than just our 2 solutions that we had. So either make a mental note, or you can change it in your calculator, but remember you're only giving solutions between 0 and 2 pi. So if you want, you can just change your window to show 0 to 2 pi. I'm going to give us that -1 just for room, but you can type in 2 pi into this. It'll instantly change it into gross decimal, but just know that it's 2 pi. So now we have our two solutions. And if we would have kept going, we would have had a third solution, but remember, 0 to 2 pi. Finding those solutions, in case you've forgotten, since way back when, you go second, calculate, and then we're going to go intersect, number 5. First curve, second curve, make your guess. I'm going to go for this one. 2.837, which is what we had before. The other one, I'm sure, would be 0.305 if you went and found it. But that's one way to use your calculator to do it. And the nice part about this is that no matter how complicated the situations are, it should be relatively the same process. These trip people up, so if you're working with secant instead, secant is the same thing as 1 over cosine. So you don't have a secant button, you do have a cosine button. Make sure you're using, instead of graphing secant, you're going to graph 1 over cosine theta as your y1, and then your y2. You can either do this, or you could flip -3 as well. So you could say -1/3. The way we have it written, we want it to be written like this. Find those points of intersections, and then you're good to go. So you could write it like this, or you could write where cosine theta is your y1, and then -1/3 is your y2. Same idea for cosecant, except with sine. So sine so your y1 would either be 1 divided by sine, or your y1 would be sine, and then your y2 would be either -3 or -1/3, finding those points of intersection. Okay. Went through those kind of quickly, so if you are having trouble with your calculator, make sure you're stopping by. But I want to leave plenty of time for these. They do get a little bit more complicated, or uncomfortable, I should say. So with these, we're going to do this with, we're going to verify with the graphing calculator. I'm going to leave that up to you, but just being able to type these in as is can be a struggle, so feel free to try that out, and then again, stop by office hours if you need to. But to solve this is a quadratic equation, but the quadratics that you're using aren't just direct variables. They're going to be sine of our variable. So it adds a second layer to this process. My hint to you is, if you're having trouble, swap out one of them for x. So sine of theta is equal to x. Okay? So factor this. So it's the same process, just x instead of sine of theta. If you're more comfortable doing it this way, it takes some extra steps, but not too bad in general. So now x would equal 0, x would equal -1/2, but we're not solving for x, we're solving for theta. So then you have to resubstitute it back in. Again, it takes an extra step or two, but if you're more comfortable with x's, it makes the process easier. Theta is equal to 0 and pi, not 2 pi, because remember our range that we're working with is 0 to 2 pi. So just make sure you're not giving me 2 pi as an answer, because it's not included. Theta, or sine of theta, is -1/2 at 7 pi over 6 and 11 pi over 6. Again, making sure it's between 0 and 2 pi. Okay, those are our 4 solutions. I'm going to do this one without swapping out x, but again, it's the same process. So 2 sine theta minus, I know it's minus because we're adding 1, subtracting 3 sine theta, so it's going to be minus and a minus. sine theta minus. The only way to get to positive 1 would be minus 1 minus 1. So that means that sine theta equals 1/2. Sine theta equals 1. So theta is pi over 6, 5 pi over 6, and then the only place that sine of theta is 1 is at pi over 2. Doesn't matter that it's out of order. I haven't checked my open math, but it might make you put them in order, which would add a little bit more complexity to it. It's nice when you can just throw them all on a list, but you don't necessarily have to organize it. All right, so pretty good, not too bad. These get a little bit more complicated. Just keep stretching your abilities and making sure that you can get those difficult ones. Luckily, number 6 is already factored for us, so we don't have to do too much there, but we're going to figure out when is cotangent negative 1 and when is cosecant positive 1/2. Cotangent, remember, is 1 over tangent, so I could flip the fraction and make it tangent if you're more comfortable with it. Negative 1, air quotes flipped, is still negative 1. So cotangent and tangent are negative 1 in the same places. And that is at 3 pi over 4. And 7 pi over 4. I don't like cosecant, I'd rather deal with sine. So sine of theta, flip the fraction, equals 2. It might go unnoticed if you are dealing with cosecant, because we're not used to dealing with it. But cosecant cannot equal negative, or cannot equal 1/2. Just like sine can't equal 2. The range of sine is between negative 1 and 1, so this portion has no solutions. Yes, we do have that possibility now, so be aware that solutions might not be possible with certain situations. Most of the time it's when sine and cosine are outside of negative 1 to 1. All right, so in this case, the only portion that was necessary was that cotangent. But what if we have this situation? So I'm going to rewrite it. 3 cosine theta plus 3, 2 sine squared theta. I'm going to go full screen. And bam, more room. Okay. So the issue here is that we have sine and cosine. It makes it really difficult to factor when we have two different trig functions. This one was already factored for us, so it wasn't a big deal at all. But this one is not factored for us, and it's going to be super difficult to figure out what we can square or what we can multiply by to get to 2 sine squared, and then add to get to cosine. But we do have trig identities, and those are going to help us tremendously in these types of problems. So I can't really do much with cosine, but I can do something with sine squared. Sine squared is part of the Pythagorean identity, and I can change it to this. Now all of my trig functions are cosine or cosine squared. So now I can factor, I can do stuff with it. I still need to clean it up a little bit by distributing that 2. And now I have something that resembles things that we've done in the past. What I'm seeing is a quadratic equation where instead of x we have cosine theta. So treat it like that. With quadratic equations, you want to get all of the terms to one side. So I'm going to add 2 cosine squared. I'm also going to subtract 2. So 2 cosine squared theta plus 3 cosine theta plus 3 minus 2 is 1 equals 0. All right, now we can just factor this. It's going to be 2 cosine theta, cosine theta, and we are multiplying to get to 1, adding to get to 3. 2 times 1 plus 1 times 1 will get us there. And this equals 0. So cosine theta equals -1/2. From here, it's very similar to all of the other problems that we've done. Really, the hard step was switching sine squared into 1 minus cosine squared. But we're past that now. So 5 pi over 6, 7 pi over 6, and then pi. And that's it. So they get a little bit more difficult. Use those trig identities. We practiced them quite a bit last week. They aren't going away. They're very useful tools within these types of problems, sometimes by design. But again, it makes it nice to be able to manipulate a problem to make it look easier and make it possible. Verifying with a grapher, make sure you're graphing the entire thing, finding points of intersection or finding zeros, all the tools that we've learned from trimester 1. But until next